When inverters are connected in parallel, their output voltage and frequency must be synchronized for proper operation. The current capacity, however, is not simply added together. In a parallel connection, the current capacity is not directly affected. Each inverter will still output its full load capacity of 21 amps. Therefore, the total current capacity remains at 42 amps. Since the inverters are connected to a panel with only 120-volt circuits, the system operates in a split-phase configuration. In a split-phase system, the voltage is not simply doubled to 240 volts like in a single-phase system. Instead, each phase of a split-phase system carries 120 volts, and there are two phases with a 180-degree phase difference. Each inverter is outputting 21 amps per phase. With two inverters, the total capacity is 42 amps per phase. Therefore, the actual capacity is 84 amps total, but this is divided into two 42 amps phases. The system has a current capacity of 42 amps per phase, resulting in a total capacity of 84 amps. This is not a simple doubling of the individual inverter capacities because of the split-phase configuration. To elaborate further on the practical implications, consider how these figures relate to circuit sizing and breaker selection. In a typical residential setting, branch circuits are often rated at 15 amps or 20 amps. With a total capacity of 84 amps split across two phases, a considerable number of such circuits can be accommodated. However, careful planning is essential to ensure that the load is balanced appropriately between the two phases to avoid overloading one side of the system. For example, if one phase is heavily loaded while the other is lightly loaded, the voltage on the heavily loaded phase may drop, potentially affecting the performance of sensitive electronic equipment. Furthermore, it's crucial to adhere to local electrical codes and regulations, which often specify maximum allowable loads for circuits and require the use of appropriately sized overcurrent protection devices, such as circuit breakers or fuses. These devices are designed to interrupt the flow of current in the event of an overload or short circuit, thereby preventing damage to equipment and reducing the risk of fire. When sizing circuit breakers, it's important to consider not only the continuous load on the circuit but also any potential inrush currents that may occur when equipment is initially turned on. Inrush currents can be significantly higher than the normal operating current and may cause nuisance tripping of circuit breakers if they are not sized appropriately. In addition to circuit sizing and breaker selection, proper grounding is also essential for ensuring electrical safety. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and energize the circuit in the event of a fault. Grounding also helps to minimize the risk of electric shock by providing a reference point for voltage potentials within the electrical system. It's also important to consider the impact of harmonics on the electrical system. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency of the power supply, which is typically 60 Hz in the United States. Harmonics can be generated by nonlinear loads such as electronic devices and can cause a variety of problems, including overheating of transformers and conductors, increased energy losses, and interference with sensitive electronic equipment. To mitigate the effects of harmonics, various techniques can be employed, such as using harmonic filters or reactors, or specifying equipment that is designed to minimize harmonic generation. Furthermore, regular maintenance and inspection of the electrical system are crucial for ensuring its continued reliability and safety. This includes checking for loose connections, damaged wiring, and corroded components, as well as testing the operation of overcurrent protection devices and ground fault circuit interrupters. By addressing any issues promptly, potential problems can be identified and corrected before they lead to more serious consequences. When integrating renewable energy sources, such as solar panels or wind turbines, into the electrical system, additional considerations come into play. These sources typically generate direct current, which must be converted to alternating current using inverters before it can be used to power household appliances and equipment. The inverters must be carefully selected and installed to ensure compatibility with the existing electrical system and to comply with all applicable codes and regulations. Additionally, it's important to consider the potential impact of renewable energy sources on the stability of the electrical grid. In large quantities, intermittent renewable energy sources can introduce variability into the grid, which may require adjustments to grid management strategies to maintain a reliable supply of power. It is also important to understand the difference between apparent power, measured in voltamps, and real power, measured in watts. Apparent power is the product of voltage and current, while real power is the power actually consumed by the load. The ratio of real power to apparent power is known as the power factor. A low power factor can result in increased energy losses and reduced system capacity. Therefore, it's important to select equipment with a high power factor and to implement power factor correction measures when necessary. Considering ambient temperature effects is also important. The ampacity of conductors is affected by ambient temperature. Higher temperatures reduce the ampacity of conductors, while lower temperatures increase it. Therefore, it's important to select conductors with an appropriate ampacity rating for the ambient temperature in which they will be installed. The National Electrical Code, or NEC, provides guidance on adjusting ampacity ratings for ambient temperature. For example, NEC Table 310.15 Bone provides adjustment factors for ambient temperatures other than 30 degrees Celsius. Similarly, directing conductors due to the number of current carrying conductors in a raceway or cable is also essential. The ampacity of conductors is also affected by the number of current carrying conductors in a raceway or cable. When multiple conductors are installed together, the heat generated by each conductor can raise the temperature of the other conductors, reducing their ampacity. Therefore, it's important to direct the conductors according to NEC Table 310.15b3. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of each conductor must be directed to 80% of its original value. Surge protection is also important to consider. Electrical surges, such as those caused by lightning strikes or switching events, can damage sensitive electronic equipment. Surge protective devices, or SPDs, are designed to protect equipment from surges by diverting excess voltage to ground. SPDs should be installed at the service entrance and at any sensitive electronic equipment. The selection and installation of SPDs should comply with all applicable codes and standards. Furthermore, understanding voltage drop calculations is crucial. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Therefore, it's important to calculate voltage drop and select conductors with an appropriate size to minimize voltage drop. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Finally, using appropriate wiring methods and materials is vital. The NEC specifies different wiring methods and materials for different applications. For example, in wet locations, conductors must be installed in watertight raceways or cables. Similarly, in hazardous locations, conductors must be installed in explosion-proof raceways or cables. It's important to select wiring methods and materials that are appropriate for the specific application and to comply with all applicable codes and standards. In conclusion, understanding the nuances of parallel inverter connections, split-phase configurations, and electrical system design is essential for ensuring a safe, reliable, and efficient power supply. By carefully considering factors such as circuit sizing, breaker selection, grounding, harmonics, renewable energy integration, power factor, ambient temperature, conductor directing, surge protection, voltage drop, and wiring methods, a robust electrical system that meets the needs of the application can be constructed.